So let's move now to Rust. Why Rust? And the key suggestion on how to write high-performance Rust. So first of all, let me open a small parenthesis on our journey on programming languages. So for what concerns me, 20 years ago, so it was almost 20 years ago, a little bit less than 20 years ago, I was doing lots of C++. And by the way, back in early 2000, I had even written a real-time Java runtime and compiler in C++ that eventually flew the first UAV, or flight control software for a UAV. So I know C++ very well, right? I like it as a programming language, but again, having a background on functional programming languages, I was always missing something in C++, right? There were certain things that I was missing that I always thought it was great. And again, there is another problem, that if you're looking for an high-performance programming language, great. High-level abstraction, great. I mean, one of the fantastic things of C++ are templates, so powerful, right? But then if you look at the number of issues that are created either because of concurrency or memory management, and the portion of those that are exploited for security, it's insane. I mean, there was a report recently from a security firm, and I believe another one from Microsoft, that stated that 70% today, 70% of the security issues are related to memory management problem. And so if you're using a non-memory safe programming language, I mean, you are exposing yourself to those problems, right? So after strong past in C++, well, mostly C++, then the first version of Zenoh was actually written in OCaml. So not sure how many of you know OCaml. OCaml is one of the ML derivatives. It's a great programming language, but delivers very good performance, very high level, memory safe. But there were a couple of problems with OCaml that at least we were facing. First of all, although the OCaml garbage collector performs very well, there was still a garbage collector, and we were still not very happy about the level of jitter that we were having on some low latency use cases. The performance we were getting were very close to C because the OCaml compiler is just terrific, but the garbage collector was just bothering a little bit. Then there was another problem with OCaml, which was the fact that back then, we didn't have support for multicore. There was very good support for asynchronous programming that for us was very good. I mean, the asynchronous framework is very, very effective, but there was no multicore support. The multicore, was supposed to be coming next year, but every year was next year. And it has been merged into the main trunk only this year. And then the last point was a matter of community. So, there are some niche. Obviously, there is a niche of OCaml developers and a niche community here in France. There is another one around in Yale. There is another one in Cambridge. But, it's not the most widely used programming language in the world. So we decided to switch. We knew we didn't want to get back to C or C++. We had evaluated Rust already in 2015, but didn't feel it was ready. And then again, in just about, I think it was end of 2019, 2020, we went back and did another evaluation. And in light of the addition and the improvement that were made with the 2018 edition of the language, we said, yeah, thumbs up. I mean, now we can really move to Rust. So let's go. And we did a complete rewrite of Zenoh in Rust. And in the rest of this presentation, I'll tell you our experience and how to get into performance. So first of all, we find that Rust is an extremely productive programming language. Sure, there is a learning curve. I think that the learning curve depends on how much you are familiar with other programming languages and how much you try to resist the rules of Rust, especially the rules on ownership, right? Versus you just decide to adopt those rules and you realize that Rust put constraint on you, and you have to carefully think of what you're trying to achieve and design in such a way that is friendly and compliant with the constraint that Rust put on you to ensure that your application can be memory safe and concurrency safe, okay? Once you do that, I mean, we are very, very, very extremely happy with the productivity and the level of, let's say, defect in our software, which is very low compared to C or C++. We had similar experience with OCaml, in which once it runs, it works, okay, which is always very good property. So the other things that for us was key is asynchronous programming, right? If you want to be able to efficiently deal with networking code, so dealing with lots of connections, and in our case, we deal usually, especially in our routers, potentially with multiple networks. I mean, multiple physical network. Could be multiple Ethernet or routing between, an Ethernet and a Bluetooth and so on and so forth. So for us, the ability of doing asynchronous I/O is quintessential because it makes our code easier to write, easier to reason about, right? And not so easier to debug, but debugging concurrent code is always complicated. And we will see what are the complexities that are inherent to async. But asynchronous programming and networking code, or scalable networking code, are almost, from my perspective, a synonym, okay? And again, one of the key points is trying to avoid, and in fact, completely avoiding inversion of control. Inversion of control, just to name it differently, is the use of callback. Okay, if I use callback, all of a sudden, my logic is scattered in several different places of my code, and it's usually very hard to understand, especially for a third party, to understand what I'm doing. If I don't have inversion of control, like in the example that I showed you early on with our query, my code looks sequential. Okay, so it's easier for a programmer to reason about it. It's easier to understand the property and the invariance, right? And that leads to better maintenance, less bug, and less pain for us overall. So in summary, right, why do we love Rust? Because it's memory and concurrency safe. So again, that improves your safety and security. And concerning safety, there was recently an announcement from AUTOSAR, which is a standardization organization in the automotive industry, that they've started a track on investigating the use of Rust in automotive and for safety critical software. So I think that's another point that reinforces the safety aspect. The second point is it has high-level abstractions. So traits, the way in which generic works, algebraic data types. It's a pleasure to work with Rust. For me, it's like a system programming language that is able to pick some of the neat part of Haskell, but maybe you see some of the Haskell book behind my back, and some of the beauty of ML languages. Because in the end, if you look at it, Rust, it is an expression language. And expression languages are really coming from the ML family. But then if you look how trait work, they are like type classes, kind of like type classes in Haskell. And then you have algebra data types. It's beautiful, it's productive, and it helps you create nice abstraction, which is nice. And this is one of the reasons why we didn't even consider Go as a programming language, because the abstraction level provided by Go is very low. You have to do everything by yourself. I believe they have just added generics, but generics weren't even there, which is really a no-go for us. You have zero-cost abstractions. So again, anything that is added in Rust is done in such a way that doesn't hinder high performance. So it doesn't let your code size grow. It doesn't let your overhead grow either. And as I mentioned before, built-in support for asynchronous programming. Again, that for me is an essential aspect for network programming. Okay, so how do you get high-performance code with Rust? And again, here the accent is mostly on network programming. So what are the usual recommendations? So I've been working on a distributed system for a long time, and people that have been working in distributed system, high-performance distributed system, high-performance network programming, know that there are a bunch of rules that you shouldn't break. It's like, your commandments, right? So if we start with concurrency, one of the errors, for instance, if you think at the average Java programmer, well, sometimes I've seen C++ programmer also doing that. they don't understand the cost of threads, okay? And even worse, they don't understand the devastating impact of having too many threads, okay? And thus the importance of having support for asynchronous programming. Again, many people think that, wow, we have this great abstraction of threads, so I can spawn as many threads as I want and my system will work great. Well, that works great on toy application. As soon as you try to scale your system, as soon as you get under load, you will get your machine trashing, and you will lose progress. Your machine will be trashing because of context switch between threads, and it will be just a mess. So the rule of thumb that people that work in this domain know is that by default you should think as if I shouldn't be used more than one thread per core. And if you're using more, you need to understand why. Because once again, if you're using, and I've seen that in some system, some software developed, Java programming is an example, but not just by Java programmer, way too many threads. That seems to work up to when you don't hit a given load and you are trashing your system just because of having too many threads that are fighting and context switching all the time. And as soon as you have too many context switch, you are dead with performance, okay? So that's the first point. It's not so much Rust specific, but again, Rust gives you a nice way of controlling the number of threads, because if you use asynchronous programming, all of a sudden, you can fix the number of thread, OS thread, and then a future that are scheduled on this pool of threads. Okay, so that's great. And you can even be more smart I won't have the time to cover executor, but you could potentially have executor that take different groups of cores and then, organize this executor for different elements of your stack, okay? Second point is limit, or as much as possible, avoid locking. So what does that mean? Well, there is certain locking that cannot be avoided. And I think the question is really, can you get by using non-blocking or lock-free data structures in that case? Because when you can, it's a good way. But think very careful on how you architect your software, because architecture also has an impact on the amount of locking that then will be required. And locking will kill your performance, right? Now, there is something else to be kept in mind, because you will be hearing that locking is always bad. There are really 2 points on this. One is the amount of locking that you have, okay? Second, well, in fact, let's say 3 points. The amount of locking that you have, whether you are locking threads or lightweight threads. So in the case of asynchronous, that's if you're using asynchronous, a lock sometimes is as efficient as an atomic operation, okay, if you're lucky enough. And then it's the level of contention. So locking with low contention with Rust async is as expensive as an atomic operation, okay, which means it's very cheap. Locking between OS threads is not cheap at all, right, because you are getting into the OS. So once again, I'm giving you some key point to recall, expanding verbally, but again, there is I think it's very good to move when you write high performance concurrent software to async, because even then, if you have to lose some locking, then if you design your software in such a way that those lock are in any case under low contention, your lock, most of the case, will be as expensive as an atomic operation, which is very cheap. The other point is limit context switches. Again, context switches can kill your performance, and especially context switch between OS threads. They will get your system trashing. So limit the number of OS threads, and then if you have context switch, think of context switch between green threads, or again, futures, because that's very cheap. Very cheap between quotes, because we will see there are some hidden traps there as well. Second point, memory. Okay, again, these are kind of generic, and then I will give you perhaps some twist for Rust. In your critical path, you should limit, or ideally completely avoid, dynamic memory allocation. Okay, so in Zenoh, essentially in the critical path, We practically avoid dynamic memory allocation, and if there is a dynamic memory allocation, it's the very end on user land, let's say, and it's mostly copy and write. So dynamic memory allocation, it's rather expensive. And again, here I mean heap memory allocation. Again, it's rather expensive when you're operating at our scale of time. If you don't care, I mean, if you are writing an application that operates on the milliseconds or seconds, fine. But then you have to be cautious of something else, which is memory fragmentation, potentially, right? So keep that in mind. The other point is that good performance need good cache behavior. And that's true for the instruction cache as well as the data cache. Not all data structures are the same with respect to caches, right? If you have data structures that are non-contiguous, and so they are using pointer, I mean, those are not very cache friendly, right? Because in a way, you cannot use spatial proximity, in order to leverage the prefetching that typically compiler and modern hardware does, okay? So think very careful the data structure you use, favor contiguous representation of data structure. For instance, just to give an example, in our routing graph are not implemented by using dynamic data structure, but they, as much as possible, they are represented in contiguous memory. Again, you can look at the code for more information. There are some nice libraries that also help you do that, but keep this in mind because cache affinity is very important, and spatial locality is super essential if you want to have good performance. Last point, which is a general rule, is measure, don't guess, right? Systematically measure performance. There are lots of very good tools. Build performance tests that are relevant to the application. If a criterion isn't enough, and if you're working with networking software, that's highly likely that you need both. Look at the raw data and do proper statistics. Try to understand outlier. Look at the raw data because sometimes there might be weird behavior, and then profile your code using perf, btune, or some of the tools that are there, okay? Now, avoid surprises. What do I mean with avoid surprises? So if you plan to rely on a library, then when you choose a library, make sure you evaluate it, especially if it's a core library. Never pick a library because everyone else uses it, okay? Because maybe they have different needs than you do. And I want to provide you a cardinal example of this. So let's look at the sync libraries. If you're into Rust, you know that everyone uses Tokyo. We use Rust async. Why? Because we measure, okay? Let me try to explain you what is the problem. So if you look at the various different asynchronous framework, and there are plenty of those, some of which are mainstream, other which are rather exotic, but the two main framework are Tokyo and AsyncSTD. The vast majority of Rust programmers use Tokyo, but Tokyo, and we have raised this to the last programming language we are discussing with the Tokyo team, has some performance issue. So here you see the latency induced by Tokyo when compared to AsyncSTD or synchronous, let's say, socket programming in Rust. And you see that this is logarithmic scale, that Tokyo kind of plateau at the level that, it's much higher than AsyncSTD. So there are, we are at 7-8 microseconds for AsyncSTD, and we are almost at 20 microsecond latency for Tokyo. I mean, that's way too much for us, okay? We cannot pay for that extra cost. And to make things worse, if you look at behavior under contention, so if we have multiple synchronous tasks running, then Tokyo completely starts misbehaving. So once again, my recommendation is whenever you pick a library, understand if other people have a use case that is really like yours, right? Because Tokyo is used by lots of networking framework, but perhaps they don't have the same performance requirement like us. And there is nothing that can replace measuring it, okay? So this is for us a tricky situation because, as you know, the vast majority, usually there is a group effect. So some people or big companies use Tokyo, everyone uses Tokyo, although Async delivers better performance. We are engaging with the community, with the Tokyo team, with the Async team. and the language team to try to sort this out and make sure that, Tokyo perhaps improves their performance, or, we make sure that sufficient work is put into asynchronicity. The last point that I want to raise, and then we'll move to questions, is asynchronous programming is great, but it's hard to profile its performance, because when you start looking at the profile, I mean, the first time you get your eyes crossed, and then you kind of get used to it. And the things that you have to be super careful is do not consider or under-evaluate the impact of the stack size of the futures on your performance. So every future in Rust is a state machine. And each time you have, and the bigger is your future, the bigger is the state machine. And as you chain call, the state machine gets bigger and bigger. The impact of this is that each time you make a call, you have to copy this state machine. And if the state of your future is rather big, obviously you have an overhead that is linear in the size of the future. You can profile that with Rust. Make sure that you look at the size of your futures. Having big future or big stacks in future will kill your performance. So watch out for that, because we'd be beaten by that once. I think we were some of the first to be beaten, and then we learned the problem, but now we share it with you so you don't have to undergo the same problem. So in summary, and there we are just about in time, the path to performance is all about a disciplined step after step journey. You have to measure, you have to profile, you have to understand, and if you don't understand, you have to keep analyzing up to when you understand. Trust me, to figure out that some of the performance problems we were having were the size of the future, was not a snap of a finger, but only the discipline and a very analytic approach will get you there. So many of the tricks that apply to C and C++ continue to apply. So if you're using to high performance computing and high performance network programming, some of the idioms and the principle will continue to apply. There are some specials, and again, some of those specials are specific to async and futures. And again, I gave you some of the key one. There are some others. Real briefly, watch out async traits, because those induce dynamic memory allocations, and so on and so forth. So that concludes my talk.